Hello, AP Chemistry students. This is section 1.4 on the composition of mixtures. This is going to be kind of piggybacking on a lot of the stuff we talked about last time in terms of pure substances and ratios. And this will be a little bit shorter, but our learning objective here is to explain the quantitative relationship between the elemental composition by mass and the composition of substances in a mixture. And kind of what we're looking at here is just thinking about what mixtures are and how we can analyze the ratio of stuff contained in them. So very often, substances are not pure. And very often that's on purpose. We make mixtures with specific purposes. Say you're making a fish tank, you want a certain salinity in it. And speaking of salt and salinity, salt water is a mixture. We have salt, obviously, NaCl, dissolved, and that becomes Na plus and Cl minus ions. And that's all surrounded by water molecules. And depending on how much salt we dissolve into that water, it's going to have a different molarity to it. And we're going to have varying proportions of our sodium chloride ions and our water molecules. But what we do know is that what if we put salt into water, it's going to dissolve and spread out, and we're going to get what's called a homogeneous or homogeneous mixture, meaning that the atoms and molecules, even though we have sort of a variety, are going to be evenly distributed in the substance itself. Another type of mixture is when we have something like a rusty piece of iron. Now, we have iron metal, or we started with iron metal, but then as it was rusting, oxygen atoms started to incorporate themselves into the surfaces, which means that we end up getting iron oxide, Fe2O3, at the surface. But since that rust is not all the way through the substance, we consider this to be a heterogeneous mixture, meaning it's not even all the way through. And to figure out how pure a substance is, how much of that substance is a single type of compound or element, we can do different kinds of analysis. So an example I have here is sodium hydroxide, which is a strong base. It is also hygroscopic, which means it has the tendency to absorb water from the air. It's kind of like a sponge, even though it's like a solid crystal matter. And this can be problematic if we're trying to do an experiment with sodium hydroxide, because if we were to weigh out a certain amount of it, we wouldn't know how much water had already incorporated itself into the solid, and we wouldn't know how pure it was. We could measure out 10 grams, but we can assume that maybe some of that mass is actually going to be water. And if we're trying to obtain a specific number of moles of sodium hydroxide, that's going to make it a problem for us. So it sometimes is helpful in that case to do an analysis where you figure out how pure something is, so then you can use an appropriate amount. And we can figure this out with some clever analysis. So let's look at the math that we can do here. So say we had 16 grams of sodium hydroxide, or what we assume to be pure sodium hydroxide. We pull 16 grams out of the container and we weigh it on a scale. And we're trying to make a solution of sodium hydroxide, which is a strong base. Maybe we need a base for some sort of acid-base experiment. But we can do is acids and bases, their concentrations are often defined by their pH, which we're going to look at much later in the class. But just assume here that the student was able to use the pH of the resulting solution to then figure out what the concentration of hydroxide was. So the sodium hydroxide, the NaOH, is going to split up into NH plus, Na plus and OH minus ions. And we were able to calculate that the concentration of OH minus ions was 0.950 molar. And then based on this, we want to figure out what the purity in terms of percent of the original solid sodium hydroxide was. So what we do here is let's first figure out, based off of the concentration, how many moles of OH minus we had. So we had 0.950 moles per every 1 liter, but we didn't have a liter. We had 400 milliliters, which is equal to 0.4 liters. Remember that to convert milliliters to liters, you're going to divide by 1,000. So the product here is 0.380 moles. So that's how much hydroxide we have in the solution based off of the 16 grams that we added. And we can assume that since sodium and hydroxide are in a 1-to-1 ratio in the formula unit of sodium hydroxide, that there's also going to be 0.38 moles of sodium. And then therefore we have 0.38 moles of sodium hydroxide as a whole, considering That's how much of the overall formula unit we have. So if we have our 0.380 moles of sodium hydroxide, we're now going to multiply that by the molar mass of sodium hydroxide to figure out what the corresponding amount in grams should be if that was how much we found in the solution. And that leaves us with the number of 15.2 grams of sodium hydroxide. So even though we started with 16 grams of sodium hydroxide overall, only 5.2 grams of that was actually sodium hydroxide. The other 0.8 grams of that was water that had sort of absorbed into the solid from the air. So to figure out what the percent purity was, we would just take the actual mass of the sodium hydroxide, divide by the mass of the solid overall, multiply by 100, and we end up with 95%. So our 16 grams of sodium hydroxide that we weighed out had 95% purity. And we were able to figure that out using the ratio of sodium hydroxide and knowing the concentration of hydroxide ions in the sample. And that is all for this one. So I'll see you in the next one.